Assalamualaikum and good morning. Hello, this is Dr. Rosmaini Tasmin again. And this morning, I would like to lecture on product development cost, titling Robust Design. This is basically chapter 12 from your lesson plan. And in this chapter, Robust Design, basically it is discussing the topic on the testing of a new design for a performance, and it is with respective noise. Okay, so basically what is robust design is all about. Okay, robust design is actually an activity in product development to improve the desired performance, right? The actual performance while minimizing the effect of noise. Okay, so it is you want to maximize the performance while minimizing the noise, right? So, for example, if you are designing for this performance to achieve the nominal value, or which is here, which is the central value, on the left that is your lower specification, on the right is the upper specification. Your performance is measured based on this achievement or attainment of the nominal values. Whether it is achieved on the net plus side, or it is achieving on the negative side, that is considered the noise on the left and right. Okay, so robust design can easily be explained to achieve the excellent design or universal design. In other words, known as robust design is to achieve the maximum performance with minimum error or minimum noise. So you have to achieve the highest performance value for a signal. For example, this is the graphic depiction of a signal to noise ratio. Okay, so for example, if you are designing a microphone, a new microphone, so your performance is being measured on this design. So how to measure a performance of a new microphone is the voice, is the clarity of the voice, the sharpness of the voice. This is your signal, right? The clarity of signal, your own voice. This is what they call the real performance. However, normally this voice or your own sound will come with a noise because the mic is picking up a surrounding noise. That is the noise. The noise may come from the wind blowing, or your neighbor's dog is barking, or your friends is talking outside the room, or the noise may come from the noise made by your ceiling wall, right? The wind blowing. So these are considered the noise, right? So your robust design or your excellent design of your mic is being judged by the clarity of the voice to be maximized, and by the surrounding noise, like your neighbor making noise, is being minimized. So that is what they call a robust design. In designing, there is a method to design in developing new product by conducting experiment, right? You have to experiment your mic in many situations, in many combinations. That is by conducting many experiments to improve the performance of the product, which is this clarity of the signal of your voice, and even within the present of the uncontrollable variation, for example, noise from surrounding. And this design is called a robust design. Okay, a robust design is basically is setting the values for certain combination of design parameter values for which the product performance is as desired under a range of operating conditions. It means that you have to create many testing for the new product so that the parameter values can perform maximum. And even though there are some variation or noise surrounding your newly developed product, it can be suppressed or it can be minimized. As such, you will have an excellent design with maximum signal performance and with the most minimum noise available. Okay. So in the textbook, it is highlighting the case study at Ford Motor Company, right? They want to test their seat belt of the passenger at the back seat, right? So even though Ford was not among the first who are designing and installing seat belt in the car, so Volvo was the first manufacturer of automobile that introduced seat belt, right? But in this case study, in the textbook, it is highlighting passenger belt performance at the back seat of a car, and they want to measure the passenger so that it is upon having a crash or accident, how far is this passenger is being moved forward, or crashing forward, or it is sliding downward, in which they call it a submarining problem. Submarining problem it means that when the car involved in a crash, so how far is this passenger moving forward, or how down is this passenger is going down? This is what we call going down submarining, right? So they want to test the seat belt with lap, right, and shoulder belt, which is this one at Ford, right? So as such, Ford has to set many points for the setting so that to avoid submarining. So many points is kind of set so that they can execute many trial and error at each of the position which is being tested. So what is the best set condition? They call it set point, right? That the passenger is having the maximum of its performance of safety when having a crash. Okay, bottom line is, in the current automobile back seat, normally what is left is this diagonal belting in the left and right of the passenger, and where else the central passenger is sitting at the back seat remains with these lap belts for protection. Okay, so that is the robust design at Ford Motor we are discussing in this chapter 12 for robust design. Okay, bottom line is what is robust design is all about. Okay, so as I informed you earlier, in order to have robust design, you have to make trial and error, many types of trial and error. In other words, you have to execute many experiments, and each experiment is being set with many different set point to determine the most optimum parameter, which is highest performance, which is lesser noise, right? Okay, in the textbook, it is highlighting this diagram. So, for example, Ford want to test factor A, right? So, and it must be tested against a factor B, right? So, for factor A, based on the testing, it shows that from A1 to A2, right, measurement, it has a linear relationship, right? Straightforward linear relationship. You increase this x-axis, and x-axis increase, y-axis, right, also increase. However, for factor B, upon being tested, you could see that B1 and B2, right? At B1 stage, it has a linear relationship. However, when it is attaining at B2 range at this x-axis, it has this exponential curvy relationship against the y-axis. So you could see factor A is pretty much straightforward, linear, and factor B is pretty much like an exponential curve. Okay, so this is what they call you have to combine the tests. In order to combine the tests, right, what is the best robust design if you combine factor A against factor B in the ultimate final product design is basically you have to choose at factor A, the set point must be set at A1, right? At factor B, the set point must be set at B1. So A1 and B1 is the combination of maximum performance, maximum signal with less noise, because both of them will generate this linear trend kind of relationship. So this is linear, move upward, and this is also rather linear, move upward, perhaps with a lesser inclined angle, right? So that's why B1 and A1 is the best set of performance in order to maximize performance and minimize noise or minimize variation, right? So if you combine between A1 and B2, you have definitely very much a different kind of trend of curve, whereas this one linear and this one is curved. So this will give vast variation. Okay, that's why in robust design you have to choose the optimum performance with minimized variation or minimized kind of change, right? So that is what robust design is all about, in which you have to test many set points, trial and errors, so that you could determine the least variation available with maximum performance. Okay, that is what robust design is all about. So let's take a look. Let's take a closer look on the mechanism of robust design. It says that robust design activity is also known as a parameter design, or you are designing the best set point for that product, as this is a method of choosing the right set point. Right, right set point is like this. You are choosing A1 and B1 as the best combination to test A against B factors, right? So however, engineers generally cannot fully model what kind of uncertainty or what kind of problem or what kind of variation or noise factor that you will encounter in the testing of the seat belt of back seat passengers of a car. So they cannot simulate everything, right? So as such, it is called that mathematical model is rather limited. So if you create the formula of this relation A and B, so it is very limited. You can test just few kind of setting. So in order to determine or minimize the submarining problem, okay, submarining problem is how far is this back passenger is moving forward upon a crash, or how downward it is sliding down, which is called submarining. So Ford want to test this kind of problem in a car crash, right? Therefore, one way to approach this through a technique of robust design, that you have to come up with the design experiment or you have to plan the experiment by few combination or many combination of set points, so that you could know what is the maximum performance with the minimum variation or minimum noise. Okay. Okay, this design is known design of experiment, or DOE, right? In the general bigger term, it is called robust design. Robust design is achieved through DOE, which is design of experiment, right? For a team, for testing team would like to apply this DOE approach, right? Which is this approach was developed by Dr. Genichi Taguchi, a Japanese scientist, professor in 1960s. He intended to improve the quality of a product in manufacturing processes. Well, you know, in 1960s, Japan has been basically experiencing the defeat in the World War II in 1945, and then in 1950s they want to improve back their industry. In 1960s, they began to start producing many products, particularly automobile car and electronic equipment, in order to regenerate their economy. So in the 1960s, many Japanese companies, for example, like Toyota, Nissan, their old name is Datsun, or Matsushita Group, they engage DOE approach proposed by Dr. Taguchi, and it significantly improved Japanese product, and Japanese product began to export to the rest of the world in terms of car and electronic equipment like radios and so on. So as such, 20 years later, so the American company began that the Japanese quality of product is very much outstanding. They can last longer, they can perform better, and yet at a lower price. So in 1980s, American companies like Ford and Xerox, right, began to embrace this design of experiment approach. So Ford company want to test their safety of the back passenger at their automobile testing for the car crash. So they decide to engage this Dr. Taguchi approach, which is focusing on noise factor, right? And the experiment to observe this performance and noise factor, and they call it signal to noise ratio, right? Signal means how clear is your performance, and how to minimize the variation or the noise of the performance. Okay, this is basically the detailed explanation of DOE, right? So by having the technical knowledge of designing the back seat or the seat belt is considered technical knowledge. How to design the best back seat, how to design the best type of seat belt car. So those are technical knowledge. However, in order to achieve the design of experiment, you need to combine both the technical knowledge and the experimentation data, right? So the seatbelt performance is a function of a passenger size and the type of collision. So in order to determine this seat belt performance, it is basically a function of passenger size, how big is the person, right? And in what type of collision type, right? That is a function. To determine the best seatbelt performance, it depends on the size of the passenger or the person and what type of collision that the car is experiencing. This is what the Ford engineers is hypothesizing with, right? Hypothesis, right? So Ford engineers could size the mechanical elements and to determine the belt attachment geometry, right? So the mechanical elements, for example, the seat belt itself, right? The seat or the attachment of the geometry of the belt, whether diagonal or whether this is horizontal. So only by that way, Ford can only confirm the best combination of tests for the new seat, right? So, for example, this is your testing. In the lead part, I highlight for testing of a new mic. Right, this is the signal or the real performance, which is the clarity of your voice. And the noise is basically surrounding noise that is captured within your voice. For example, the noise that your neighbor makes, or the noise that the neighbor's dog is barking. So these are noise. So this is your mic, right? So in the design of experiment, you want your clarity of voice to be always at this mean value, right? So if your voice is achieving at this point or at the lower point, and that is mean by noise. So how far it detect and detracts from the central mean value, this is a noise, right? This is the distance from this point to this point is considered a noise. So in other words, to have a clear, crisp, very sharp noise, very sharp signal, it must always be at this mean value. So if it is higher or lower, so that is considered the noise. Okay, that is what we are about to explain, the mechanism of DOE, how it is being done. Okay, so in other words, Taguchi loss function, or the DOE method introduced by Dr. Taguchi, is considered a new function of quality, right? Well, if you have a new one, so of course you have the old one. The old one is the traditional loss approach, which is this diagram on the left. The Taguchi loss function is shown on the right. Okay, so in the olden days, we get used to measure quality function in this kind of diagram. Okay, For example, for the sake of the discussion, your company is producing this steel rod, right? This kind of steel rod, perhaps for the printer, right? As a guide roller, right? This steel rod has a diameter of 5.50. In the olden days, the traditional loss approach say that if this steel rod diameter is measuring 5.50, of course that is excellent, right? And then you produce another one. If the iron rod, this is measuring slightly bigger, like 5.53, and then it's still okay because you still can send your product to the customer, right? Even though it is slightly bigger because your upper specification limit is 5.5, right? So you produce another rod. So say the diameter is 5.43. Yes, it is slightly smaller, but it is still within the specification limit. So it is slightly bigger or slightly lower, it is not lost to you. So it is still can be sent to the customer. It is considered a loss to you if it is producing bigger than 5.55, because your rod is definitely big. You cannot send to customer, or else customer will reject it, and that is a loss for you. So if you produce a very much smaller iron rod for the customer, like 5.43, that's considered a loss because the iron rod is too small. You cannot send to customer for the assembly. So that is a loss for you. So as long as it is between 5.45 cm and up to 5.55 cm, it is considered a profit for you because it still can be used and it can be sent to customer. Okay, because that is the traditional loss approach, right? However, if the rod is a bit bigger, definitely if it is being sent to customer, the clearance between the rod and with the housing, the clearance will become smaller, right? If it is a moving part, definitely it will produce many friction, and friction can create heat, and the heat will contribute shorter lifetime of the product. But in the traditional loss function, this is still not a loss, right? It still can be sent to customer. It's still gain for you. So after time pass by, Dr. Taguchi thinks of other way of managing this kind of variation, right? If this rod is slightly bigger, definitely it still work with the customer assembly equipment. However, it is kind of tight, right? So Dr. Taguchi think that that is not right for customer. What if this iron rod is smaller, which is slightly here? So definitely this iron rod will fit into the housing of the equipment with some kind of looseness. There is kind of wobble, or there is a kind of like shaking between this iron rod with its housing because it is produced smaller. And Dr. Taguchi think that kind of situation is a loss for the customer, because this vibration, this kind of looseness will definitely affect the performance in the long range. That's why Dr. Taguchi shifted this diagram from this. They change it. He changes it to this diagram, in which he introduced a quadratic curve, like this curve, and with the central nominal value right at the center. So he believed that all iron rod produced by your company must meet this target specification at 5.50 cm. If it is slightly smaller, for example, 5.4, like 5.46, right? If it is at 5.46 somewhere here, so there is a looseness there, and it's still considered a loss. However, in the older function, the loss, or you cannot ship to the customer if it is bigger than 5.55. However, Dr. Taguchi put it a very much stringent requirement, even though it is at a 5.46, is still considered a loss to customer, because customer will experience a less efficient assembly into their equipment. Okay. Dr. Taguchi believe also is that if this iron rod is produced with slightly bigger, like for example 5.53 here, right, that iron rod is still possible to generate loss to customer, because it will create a slightly bigger iron rod. When it is assembled to the housing of the printer or the equipment, it will create a tightness, and that tightness, if it is a moving part, it will create friction, and that friction will create unnecessarily high temperature, and definitely in the long run it will affect the whole operation or the whole performance of the equipment. So that is what Taguchi loss function is all about, in which loss is measured when it is divert, which is deviate from its target value. Even though as small as like 5.48 is still considered a loss to customer, right? So if it's slightly bigger, it's still considered a loss. So the loss coverage in which to customer is still measured, even though it deviates slightly. Whereas here you deviate very much, still not loss until above 5.55. And if you deviate slightly, become smaller, it's still not a loss until it is smaller than 5.45. This is the better or the greater strength of Taguchi loss function, in which it will ensure the manufacturer always produce every single lot of iron rod at the target specification value of 5.50, which is exactly here, right? So as such, all product must be produced to spec, which is at the target, else it is a loss if it is here or it's here or even here, right? Loss starts when it deviates from the target value. So that is the idea or the approach produced or mooted, generated by Dr. Taguchi. That's why many Japanese companies is embracing this kind of approach. In the overall perspective, I strongly believe that many of you would agree that Toyota or Japanese car are very much better in performance of American car, right? So we generally believe that Japanese car are very much more reliable than American car. So that is one of the difference that it creates in the overall industry and quality performance. So how to achieve this robust design capability? What are the process it takes to achieve this good robust design, which is maximizing the performance while minimizing the variation? First, as it is discussed in the book, so it is we need to highlight, or we need to identify what are the control factors, right? The performance factors, and what are the noise factors, and what are the performance to measure. Secondly, then we have to formulate the objective function, right? What are the function to achieve, and we need to come out with the design, many design plan to experiment, and then we execute the experiment, and then we conduct the analysis and select or firm up what is the final set point, the best to maximize the performance and very much minimize the variation, or in other words, maximize the performance and minimize the noise, right? Maximize the signal and minimize the noise, and do some reflection what you have achieved, what you have not, and repeat the process for the next cycle of testing and experiment. Okay, so let's take a look the step one by one. Okay, say Ford engineers want to test their seat belts and their seats in order to measure the submarining problem during the crash, or the back angle of the passenger when it is being involved in the crash, how far it moves forward, right? So Ford engineers has to decide what is the control factor. Okay, what factor to control? For example, the webbing stiffness, right? So if you take a look on the seal belt structure, right, the surface, it has the crisscross, or it has the slightly different webbing kind of patterns. So this is what they call webbing, and this webbing will determine the stiffness of the belts, right? And this factor, factor A, is being tested against a friction coefficient, right? So if the webbing pattern structure is kind of coarse, right? So it's a hard kind of webbing structure, it will give a friction coefficient to be higher because the surface is rough. So when it come contact to the clothing of the passengers, it will kind of there is a holding factor higher for that. It means that the coarser the webbing, it will be influencing the higher friction ratio between the belts and the passenger. Okay, that is the control factors. Then we have to determine the step B. We have to determine the test experiment of the noise factor. What are the noise? If this is the signal, right? And what are the noise? The noise is being tested in the form of shape of the seat, right? This shape of the seat, right? Whether it is inclined, whether it is thick or whether it is thin, against the seat fabric, right? What type of fabric they use? Is it a polyester? Is it a cotton? Or is it a semi PVC and so on? So the noise factor is tested between the shape of the seat, right? This back passenger seat and against the fabric. So it means that if the seat is curvy, ergonomics, right, it is tested as, again, the type of cloth or the type of material that the seat is having, right? So it is another noise factor to test against the control factors. And then step C, actual product specification of interest in experiment. So is actually what are the parameter to achieve in order for this testing to execute is how far the passenger back and buttock move forward. How far is this kind of movement is being detected, right? Okay, how far is this movement back angle, which is at the resting place, the back side? How far it is moving forward, right? How far is this hip and buttock moving forward, which is considered submarining? This is the performance metric that Ford want to measure. Okay, so let's take a look on the next step, which is a step which is identify control factors. It is continuation of step one. So as such, we are able to create the consolidated parameters diagram, or they call it P diagram, parameter diagram or set point diagram on all factors and metric they want to measure. Okay, so they come up with this kind of P diagram, control factor, where belt webbing stiffness, belt webbing friction, lap belt force limiter, and so on. That is the control factor. And then it gives effect on the passenger restraint process, passenger kept at their place during the car crash. And what are the noise factor want to measure? For example, shape of the rear seat, okay, type of seal fabric, right, severity of the collision or the condition of the collision, and so on. So in this case, control factors are being highlighted like this, right? The prime control factors and the prime noise factor are being highlighted like three of these. And ultimately, control factors and noise factors combined in the crash. What are the metrics? What the ultimate result that Ford engineers want to measure, which is the back angle. How far is the passenger is moving forward, right? From their inclined angle at the back seat. Okay, so this is consolidating the step one, identify control factors and noise factors, and the final outcome of the testing measurement. So in this DOE, so we have to create many test experiment with different type of set point parameter. Step 2, so we need for engineers need to formulate an objective function. First, performance metric, right? So performance metric is this, which is the outcome of the testing, right? And must be transformed into objective function that relates to the desired robust performance, right? There are a few types of objective function. One, type A, this objective function you want to maximize it, right? To maximize the performance, to maximize this, perhaps back angle, right? So definitely in this kind of objective for the backseat passenger car test, you want to minimize, right? You want to minimize the back angle, which is the movement towards the front. Okay, so in this kind of test, what engineers want to minimize the back angle, so they must achieve the objective function minimizing the type function, which is performance dimension where smaller is better. The smaller back angle is much better, right? Or you have a function of target value type. Value closest to a target best amount, right? For example, amount of back belt slackening before restraint. Or you have a type function of signal to ratio. This is one important way to measure robustness. So you have to decide what kind of objective function you want to achieve. And in this case of Ford back passenger seat belt testing, they want to achieve type function B, which is to minimize the back angle. Now, in step 3, you have to develop what kind of testing combination you want to make, right? Because design of experiment is involving many types of tests, and each test is unique. You have to set different set point, different parameter, different performance, different noise type for each of the testing condition, and only that you could achieve the best maximum performance with the less variation or minimize the noise. So one type of experimental plan is full factorial matrix. Okay, for example, A1 and A2, you test all the set point, right? A1, A2 got two types, B1 and B2, right? B1 got C type, C1 and C2, right? And B2 got two type, got C1 and C2 setting, in which you test all the combination, which is quite time consuming and also very costly. And it takes many resources to test all the nitty gritty single different type of combination, right? This is quite costly. So they call it full factorial metric. You test everything, every single different setting, parameter, noise, and set point, you test it, right? Another type of testing is that fractional factorial matrix. Well, you test half of it, only 50% of the combination you test, right? And the third type of experimental plan is you test every 16 of them, right? Which is 1 over 6, right? Every 16 test combination you test, right? Which is lesser kind of combination of tests. Or you want to test one factor at a time. For example, you want to test only A1, B1, C1, and then only one thing change, right? This is one factor at a time test, which is again time consuming, highly costly, and takes many resources. So as an engineer, you have to test it, which is the best combination of experimental plan suited to your timing, target date, I would say delivery time, time set by management for launching and so on, right? So you have to decide whether the best is half fractional or the best is 1/16 fractional factorial matrix, right? So as engineer, to achieve this robust design, you have to decide the best experimental plan. And then you have to execute the experimental plan that you have decided. right? The product is tested under this various treatment, different type of trial and error, or many types combination of experiment, and each of test experiment you capture the data, right? So, for example, the product is tested under various treatment conditions described by each row of the experiment. For example, for this each row, right? There are 7 factors you want to monitor, factors on performance, right? And there are 7 there are 7 factors, and there are 8 levels of variation, right? At A, you set the value at 1, at B, set value at 1, at C, set value at 1. On all these 7 factors, level 1 to be tested. And then you will have the noise, the compounded noise that is measured, the minimum and the maximum. And then you measure the back angle movement, what is the average back angle, what are the range of variation of the back angle. So each row must be tested, right? So each row, these all got to be tested because that's the experimental plan. Okay, so remember your performance metric is here, back angle. So these are the important outcome to measure, as this must be at the minimum level because you are choosing for the minimum type function. And next, after executing the process, you got some sort of a result. So you have to analyze the result, conduct the analysis, right? Computing the objective function is to minimize this average of a back angle, which is this is the average testing result, right? 8 of them, and these are the range of the measurement of the 8 testing that has been executed. Okay, so this objective function metric is completed, and then you need to compute the factor effect of analysis by means of angle. So you plot the higher value to the lower value to the higher value. What are the range? So this is the line diagram of the average, which is taken here, and this is the range of back angle measurement, which is derived from here. So now you are measuring A1, A2. A1 is minimum, A2 is maximum, B1, B2, this is maximum, minimum, C1, C2, D1, D2, E1, E2, which is from this factor, F1, F2 from this factor, minimum, maximum, and G factors. So this is minimum and maximum. So from there, of course, since this is a minimum function type, so you must have the minimum movement of back angle, then your best minimum set point combination for your testing is A1, okay, B2, C2. Okay, since this is flat, perhaps this is of non-different value testing. F1 is this, G1 is this. So these are the minimum best combination of set point for average of the back angle. So you take a look on the range of the minimum measured value of set point, which is A2, right? So B2, which is B2, is this combination, C2, D1, E1, F2, and G1. So as a result, since you want to achieve the minimum back angle movement, so you have to make decision. The best set point is A2, B2, C2, D1, E1, F2, and G1. So from this, you can have the best performance with the least minimum, I would say, variation. Okay, the best, the maximum signal with a very much minimum noise. Okay, by that you will achieve step 6, which is select and confirm the factor set point, because all the set point have been set, okay, by this, right? 7 factors you want to measure. There are 8 level of setting or set point that you want to make. You want to record or measure the noise, and this is the performance metric that we have to measure to decide the best set point. As such, at step 6, we have to select and confirm the best factor set points. So as such, Ford engineers decided to have the minimum back angle the set point of the testing must be set at A1, B2, C2, D1, E1, F1, and G1. Okay, so that is the best set point or the best set of trial and error experiment to achieve the minimum back angle. So after you have this, what you're going to do? So you have to set during the actual car crash with the actual fault car, with the actual perhaps mannequin of the passenger at the back seat, and you set the set point at this parameter A1, B2, C2, D1, E1, F1, and G1, and put in the testing car, put the mannequin, and run the car at certain speed and make the crash. So then you can verify that this is the optimum, the best combination with verification of the physical test to achieve the robust performance. That's how it is get done for robust design in order to test a new product for the best performance with the minimum variation, in other ways, to achieve the best signal, the maximum signal with the minimum noise. So the next step is you do reflection whether you have achieved what you wanted, and you could repeat to the next car crash performance test. Okay, by that I will wrap up this chapter on robust design. I hope you have understood how to achieve robust design, what is the robust design, the mechanism of having it done, and so you have again a good understanding of the chapter. And again, I would like to thank you for your attention, and until I see you in the next lecture. Thank you again, and goodbye.